Last class we were discussing about Radwitz. And I remember the context. We are discussing about how to visualize data that have more than 2, 3, 4, 5, 6 attributes. We are behind the limit of 3, and we need some artificial, let's say, solutions for that. We saw parallel coordinates, we saw Radwitz, and I will go ahead in this direction, showing you other well-known solution for representing what is called the multidimensional data. A very common visualization is called the star plot, or it is called the radar diagram. It is somehow similar to parallel coordinates in the sense that all the coordinates of the data set are available on the screen, but they are put in a radial fashion, on a circle. So we are discussing here, we are presenting data about students, and you have the score of the students in mathematics, in physics, in literature, history, blah, blah, and his performance in sport. So you put on each axis a single point representing the value. This is the score in maths, this is the score in physics, this is the score in literature, this is the score of geography, and so on. And you represent a single student as a polyline connecting all these values. So a single element, a single item, a single student is just a polyline. An important point is that in this way, you can recognize the shape of the student. For instance, this one is a shape representing a student that is very good in sport and is very good in literature and history, while it's not very good in physics and math. Here instead we have someone that is very good in art and in mathematics and physics, but not very good in sport, and so on. So you can compare easily 2, 3, 4, 5 students. This solution is very often used in commercial websites in which they describe the characteristics of a product according to 6, 7, 8 classification attributes. It is very effective, but it has a problem. It does not scale in the sense that you can represent tens of elements, not thousands. So unlike the scatter plot, you are limited in space here. You can use what is called a small multiple, meaning that you can repeat, because the shape is visible, you can have a lot of them, a number of them together. I will show you some image, but in any case, you cannot scale more than 50. 100 is the maximum limit you can have for that, but it's too high in any case. But you got the point. And it is good because it is scale about concerning the number of attributes. You can have more access here, and you can represent some statistical value. This is maybe the average or the score or whatever. You can compare more polyline. I will show you some real system using this solution. If you have question, please raise question through the chat, or using the audio. Another very common solution is called the scatter plot matrix with the acronym SPLOM. What is the idea? You take the data set and you put on a matrix all the possible combination of pairwise attributes. Here we have a data set that is about some chemical sample containing magnesium, potassium, thorium, uranium, and so on. And on each scatter plot, you have a couple of it. This is For instance, magnesium with potassium, this is the corresponding scatter plot. Note that the scatter plot is symmetric. You can not show half of it, or you can dedicate it to other pieces of information. In this case, we are duplicating the information. This scatter plot and this scatter plot are exactly the same, a part of a rotation of the two axes. And what you can get from it? You can get some kind of, let's say, this is a sort of inverse correlation, in the sense that the low values of magnesium are associated with the range of value of potassium, and after that the potassium is somehow constant along this axis. Basically, you perceive the distribution of the data. You can have this is a correlation between uranium and thorium. It is something that you can expect in that. And here there's still a correlation, but somehow less evident. You have a cluster here, and you have these shapes. C shape, U shape. This is a rotation. You can see, for instance, that potassium is typically a low value. A low value when you compare it with spot, whatever it is. The distribution of spot is very wide. Instead, the potassium is concentrated in a very low values, and so on. And what is the problem with this idea? Is that the number of scatter plot you are plotting on the screen increased by n raised by 2. More formal is n by n plus 1. And quickly you get an image showing a lot of this scatter plot. And there is an old idea of 2005 by Wilkinson and other people that got the idea to reduce the number of scatter plots you show to the user according to their relevance. If you have something that is not showing nothing particular, you can exclude it from the visualization. And they went for classifying some possible shape of the scatter plot. Like this is an inverse correlations, for instance. Here is a constant value of an attribute, and so on. You have U shape. Using these shapes, you can filter the data. A lot of work has been done on how to explore this potentially high number of bidimensional scatter plot. And another point that is quite obvious is that the analysis that you can do is just limited to pairwise element. You cannot go for having 3 or 4 or 5 comparison attributes at the same time. And you need some sort of interaction. Each scatter plot contains all the data. So you need to link and brush different scatter plots. Maybe you, for instance, you browse here, you select the subset of this scatter plot, and you see that items highlighted also in the other ones. You need the link, otherwise you cannot recognize single elements. For instance, just to be more concrete, here I see 2 outliers. Maybe you see it on your screen. With the advantage of remote teaching is at least that you have a high resolution screen in front of you. You see these 2 outliers. I can select, and where they are in the other scatter plots, I can brush on it, highlighting them here, and they will be highlighted also in the other scatter plot. This is a very common solution. Let's move to another kind of plot in which we have multidimensional data, but basically data is categorical. So you're representing not the data values, but some aggregation of the data. For instance, this is an example from the Titanic disaster. And basically you have a data set in which you have the this information about passenger, the age of the passenger, split in adult, child, the gender of the passenger, male and female, and the class in which they were traveling, first class, second class, third class, or people belonging to the crew. And for each of the partition you can have, you have the number of people that are inside. And one very relevant classification is also the survived one, people that survived to the Titanic story and people that didn't. You can see this table. You have the number, for instance, concerning the first class, concerning male, adult male, you see that 118 people didn't survive. Instead, 50 people survived, and so on. How can figure out visually the story? If the question is what is the most likely class that can survive in the story? If you can be a person here, which rule you prefer be in first class, second class, third class, or and so on? Mosaic plot is intended exactly for answering this question. And the idea is to take the full data set containing 2,201 people in the Titanic and to start to partition it visually. For instance, we can partition the people on the Titanic by the class in which they were traveling, first class, second class, third class, and crew. You get already an insight. You see that first class and second class are somehow balanced visually, you see, and that the third class is double than first class, and that a lot of people were in the crew part. This is still real in the modern yacht, in modern traveling or big boat. Half of the people, a little bit less, is just a crew. Passengers are half of the people on the boat. So you have a partition using this attribute, the class. After that, you go for splitting them in male and female, and you get this overview. And here you have another intuition that the crew part, as you can expect, is basically done by men, and we have a few women here, while the number of women increases in percentage, I mean, with respect to the male, along the classes. This is also another insight. And as long as you move from people traveling from duties to people traveling typically for fun, the percentage of female increases. And after that, you go for, and you are using two colors here to distinguish the two classes. After that, you go for applying the last classification you can have, that was child or adult, and you can split here I'm enlarging it in the part child and not child, and eventually the color green is coding people that survived, and the color black is coding people that died during that story. And you can start to reason on it. You can discover that in first class, basically, most of the female survived. And all the child survived as well. And the percentage of men that died in the story is somehow comparable among the different classes. But the percentage of women is quite different. You can see that in first and second class, most of the women survived. In the third class, it was about 50%. And you can argue about the reason for that. Maybe that people in first class was more polite, lady first. and that was changing, moving towards the third class. Or maybe that the situation, the pressure of the story was perceived first in third class. They were below, in the low part of the boat. People in the first class instead had more time to arrange themselves. I don't know. You can speculate on that. In any case, apart that this is a somehow sad and charming data set, in my opinion, it is interesting that this simple data set is still used by people for inventing new visualization. More or less, every new conference about visualization, someone come up with new ideas for representing this data set. The point is that the data set here is categorical, basically, and that you are representing some aggregate value. In this case, it is the count. How many people are in this partition? And let's move towards, we have several possibilities. And let's go to something that is somehow less explored, icons. You can use icons to represent some attributes in a way that it can be easily perceived. There is a very nice study about that. It is called the Chernoff phase. I'll show you what is the idea. Chernoff studied the shape of the face, and he came up with several attributes that you can use to represent something, typically something that is categorical, or no, better, ordinal. You use icons, emication in your email message and whatever, and you can use still attributes in it, and that conveying different emotion and maybe different ordinal value. I'll show you an example. The idea is to represent the life in Los Angeles, basically encoding 4 attributes. The affluence in different parts of the city, where affluence means benessere in Italian, the unemployment percentage, the stress, and the proportion of white and black population. And basically, for each of them, you are encoding 3 ordinal values. Is the benessere affluence good, average, or bad? Is the unemployment good, average, or bad, and so on? And for instance, the high affluence, so a good situation, is represented with a rounded face. The medium in this way, the low, so a bad situation, with this long shape. And the same for unemployment. Low unemployment, you are smiling. Medium unemployment, you are in the medium. And high unemployment, a bad situation, you are not smiling at all. And you know these faces. This is very common in your email. And you can see very quickly that you can perceive the better areas. Here, a very nice situation. You are presenting a good values for everything, more or less, while these faces are representing bad situation. And this relies on the idea that you can easily recognize. This is giving you the happiness idea. You know what I'm talking about. Another possibility is to encode visually some other piece of information. For instance, concerning houses, you can represent the size of the garden, the presence or not of a garage, the fact that you are dealing with a house or a flat, and maybe you have also houseboat houses, and you can represent the heating of the house and the time to walk to the Victoria Station, that is the underground station of these houses, and you can quickly compare faster different houses. This is it has a bigger garden. It has an higher number of bedrooms. So this is a houseboat, and there is no garage in it, of course, and so on. Some studies demonstrated that icons search was 200 times faster than just using text. However, in spite of their potentiality, icons are very good in representing basically nominal, ordinal, or cardinal values, and not numerical ones. And somehow they're not used very often. I saw very few solutions relying on icons. Let's move to something that instead is more powerful. Multiple coordinated views. The idea is to represent each attribute of the data set. We are still talking about houses, having each attribute represented with an histogram. We already discussed that. Here we have an histogram representing houses, where each single house is an element of the histogram. It is discrete, and you can easily scale because you can go till the pixel if you want. So you can represent a very huge number of this histogram. However, the height of the histogram is representing the number of houses in that range of price. Here we have the price attributes ranging from this value to this value, and here there is the distribution. Maybe you can perceive a sort of Gaussian in that. And a part of describing the distribution of the data, you can start to interact with the data. You can filter it. Remember that one of the typical activities after you get an overview of the data, you go for zooming in the data, selecting a subset. For instance, here I'm looking for houses that are in this price range. Houses satisfying this constraint are in green. Houses not satisfying it are outside. And you can combine, this is a single attribute, you can combine this idea with several attributes. Here we have the price, we have the number of bedrooms, we have the size of the garden. And you can see that if you select a range in price, we have highlighted all the houses satisfying the same condition according to the bedrooms, according to the garden size, and so on. Remember, each house is represented in all of these histograms. And you see that, for instance, that there is a constant value in more or less in bedrooms, while there is a varying values in garden size. And you can combine different queries, multiple selection. For instance, you can say, okay, I want to look for houses having this range of price from year to year, and having between 3 and 4 bedrooms, and having a garden size of this size. So you get this number of houses. You can see still some houses. In green, you have houses that are satisfying all your constraints. Maybe that having some numbers here summarizing the total number of houses satisfying your constraint is a good idea. And you can see that you have some guidance in this visualization. Greenhouses are houses representing the houses satisfying all the value, all the constraints. Black houses are houses that are satisfying all the constraints but one. So here there is a an house that is very close to your query, but it is missing one value. One of these three constraints is not satisfied by this house. And after that, you go with gray. Gray is representing houses that are not satisfying two constraints, and white is representing houses that are not satisfying all the constraints. Note that this solution give you a clue, a guidance. Consider this house here. It is not satisfying one constraint because it is black, and it is outside the range of this query, of this selection, meaning that this attribute is exactly the attribute for which the constraint is not satisfied, meaning that if you move a little bit this range of price, including this house, this one will become green. So you have some guidance for including in the result houses here, houses here. If you go for less bedrooms, or if you go here for till here for more little gardens, you can get more houses, and so on. Here there is no guidance for gray and white. For instance, here we have inside here we have a black house. This house is not satisfying one attribute, and this attribute cannot be priced because it is the right interval. You don't know if these houses are failing for bedrooms or garden size. No information about that. And the same for the white. In any case, about the white, even if outside, you see that this white is outside the price. So it is not satisfying the price range. But it is not satisfying three elements, so you need to amplify all of them, and so on. You have a limited but useful guidance in it, if you remember the notion of guidance. In this example, you were so selective in your query that this range in price, this range in bedroom, and this range in garden size will result in an empty data set, an empty answer. No house is satisfying your constraint. But if you here you relax a little bit your query, for instance, putting a little bit more money, you will include this black is not in the result, but it is just failing for the price. And because it is very close to your limit, that means that just moving it a little bit will include it. The same for this. Here there is a very little garden in black that if you are good with the moving your range a little bit on the left, you will include it, and so on. That can give you the idea that you can be more sophisticated in giving indication, guidance, ideas. And in the next class, I will show you something that we did in our research group to have a very sophisticated guidance based on statistical distribution and box plot and numerical and visual indicators. But basically here I wanted to get the point. Here there is a guidance towards how to increase the number of elements in the result. But this is not the unique guidance you can have. Maybe if you have too many houses in your result, you want to proceed the other way around. You want to reduce the number of houses. And yet you don't have this information. You don't know how to restrict the query. Of course, if you move the price on the left here, spending less money, you will kill these houses. But you don't know what will be the effect here on the other. I will show you something more powerful than that, but I think you got the idea. Guidance is really important. Let's just, we are going to the end of this part about representing multidimensional data. And among all the solutions we see, this one with icons, this one with partitioning the data set, scatter plot matrix, star plots or other diagrams, Radwitz, and parallel coordinates share the fact that they are representing somehow the original values of the data, and they scale with the data itself, with the number of data. This is the main point. Here we have some overlapping of data, but you can have hundreds, thousands of elements in this drawing. The same does not hold for this solution, for instance, and also for this, we will be crowded of the dimensional scatter plot. So somehow parallel coordinates and the Radwitz are not, no, I don't say the best, but are very often used for multidimensional data. And they want to show the complementary advantages and disadvantages that they have. What are the disadvantages of parallel coordinates? The cons. They are not traditional. It is not traditional representation. The first time a person is looking at the parallel coordinates, that person is somehow disappointed. It is confused. You have data crossing. You can see here. Data crossing is a very bad point, and you have some ambiguity here. You have a line entering here. Remember, one car in this example is a full polyline, touching all the elements here. If you are here, you don't see what is the next, and also here there is some confusion. So typically you perceive trends, clustering, and you have also cluttering, but you don't perceive easily single elements. And it is a disadvantage. It is not easy to interact with it with a pointer. To select a subset, you have to deal with the 7 axes. What are instead the advantage, the big advantage of parallel coordinates? You can see detail about values. You can figure out the number of cylinder, the power, the figure, the numbers. And there is a unique correspondence between data and screen polyline. A single polyline is representing exactly a single element in the data set. Concerning Radwitz, advantages and disadvantages are perfectly symmetrical. What are the advantages of Radwitz? It is a traditional representation. It is a scatter plot. You are familiar with it. There is not data crossing. There are not crossing by lines. You can easily interact with the Radwitz with the pointer. You can go for data manipulation. With the mouse, you can select a subset of the data. And you can have details about attributes, but not values, but only proportion. Remember, the information of Radwitz about attribute is about the magnitude of the attribute with respect to the other, the proportion, not absolute values. And here I put a might, because this information can be hidden by the arrangement of the attributes along the circle. We discussed that in the last class. And what are the disadvantages of Radwitz? That the first one is that the normalization and the mapping on the screen does not preserve Euclidean distance. Points that are far away in the original space can be differently plotted on the screen. So the Euclidean distance is not preserved. It is not a linear transformation. The attribute disposition around the circle affect the plot effectiveness. We discussed that in the last classes. You cannot have any clue about the original dimension values. If you are lucky, if the distribution, if the arrangement of the attribute is good, you can get the information about the proportion, but not about original values. And at one point on the screen is representing totally different points. If you remember this example. This point here, a single point on the visualization, is representing all the possible values in which A is 9 times B. The proportion between them is 9. 0901, 009, 001, 00009, you got the point. An infinite number of points, of data elements are colliding on this value. Totally different proportion. Totally different values. Exactly the same proportion. Having said that, we stop for a moment about the discussion of the data. Till now, we discussed about values. Single value, 2 values, 3 values, multidimensional data. We're talking about numbers. Now we move to the encoding of relations that are linked between numbers or relationships that are links between items. So we are talking about encoding of relation and relationships. And we'll see how to go for lines, how to have a map on diagrams, Venn diagram, trees, very common visualization means. And I will go for the sign to summarize what we have here for a representation. So, first point, we want to encode relations and relationships. Remember that here I am stressing the difference. For me, relation here means relationship between numerical value. It is a subset of a Cartesian product between two sets. And for instance, a relation is an association between 2 or more values. For instance, this is a relation among the name of the maker, the price, the consumption, the rating, and age of a single car. This line, this tuple in the relational model is representing a single car. That's why it is called the relational model. Or here we have a connection between this value that is represented as a position in this bar graph and the picture of the car. What is a relationship instead? A relationship involves 2 items. John, it is a person. He has an account in the Stingy Bank, and he is owning a Bentley, an old Bentley. Or you can say that XY, X2, X3 are childs of Y. And what is, in your opinion, the main difference between these encodings? What is that make basically relations and relationship totally different? Think a little bit about that. I don't go behind in the next slides to get the solution. Think a little bit. What is the difference between this encoding and this encoding? What are the possibility of relations and relationship encoding? Ideas? Okay, no ideas. What is the main point? Is that relations are about numbers. And having a relation, you can use the value of the number to represent the relation. I'll show you. Here we have encoding a relation among the values of a single student, the value in math, the value in physics, the value in literature, the value in geography, and so on. You are representing values on the screen. This line is an axis. It is representing numerical values. And hitting a single value, you can represent a polyline representing a relation. Or here, you put the x and y axis, you put a single house as a point, and you are using the values of this point to represent a relation between these two attributes. You cannot do the same for a relationship. If you want to show that John is connected with the stinky bank, you are talking about two entities. Think to the entities relationship model. So you need something that is connecting two abstract concepts. You can use a line, like here. John has an account in this bank. John owns this car. It is the same formalism used in UML for that, or in the entity relationship diagram. You can use the position, like this. I should have an example. No, not anymore. Here, you're using the position for aligning numerical values, but you can use the position also for aligning John and the car its owns. You can use the brushing. You can touch an element, you can get the bank connected to that person, but you cannot use values. Of course, you can use line, position, and brushing also for relation. So take care of this idea and think that now we are representing not the values, but the relation or the relationship between or among values. I'll show you some effective idea. Lines are very effective for representing both relation or relationship. Here we have a nice picture, quite informative in my mind. We are talking about people a long time ago. We are talking 600 after Domina, and we are talking about fight. In that period, the people in that part of England were really aggressive. They are fighting each other very frequently. So each line here is representing that in that year, there were a fight between the West Saxon and the Britons. And the color denotes which is the aggressor, and the green denotes the attacked. And you can easily see the frequency of this fight, and you can see people that were really kind and polite, like Britons, that basically they were attacked every time, but this case. While you can see that the West Saxons were really aggressive, they basically initiated the most of the fight that we are discussing. So you use the line to show a relationship between two categorical values or two items, and use color for encoding something. Basically, we are representing a relation, and we have a position for the time and the color for the role, for the categorical attributes. Aggressor or attacked person. What about phone calls? You have an originator and a receiver of phone calls. Again, you can use lines for that. Typically, these kind of graphs are very crowded. I will give a class exactly about the social network and let's say graph drawing for social network. But you can have some partitioning algorithm that can provide a better information of how the distribution of the data is. And you can go towards more modern visualization, but I want to start with the initial story. The radial graph, what is a radial graph? Basically, the idea is instead of putting the nodes of the graph everywhere in the plane, we put the nodes on a circle. And we try to give some order to the link, avoiding full crossing, like here. Here, also here, the nodes are on the circle. But here you connect the nodes without any kind of order. Instead, in the radial graph, you try to put some order in it. Here we have a representation of a mortgage activity. Mortgage is a hypotheca. It is very unlikely that you know these terms. I was uncomfortable with them myself. And you have the mortgage, the lender, the surveyor, the applicant, and the accountant. And this is the Italian role for them. And they are basically put on the border of this diagram. Each point here is representing a single surveyor, a single applicant. And if you zoom in, you can see a semantic zoom solution in which you can read the name of the person. This is, I cannot read, okay, it's very little, but you can get here the name. And you can see the link starting from here. And there is a solution that you put the link in internal circle to avoid full crossing here. This was the old idea. And this is real data. And in this story, there was a fraud. Some people is taking money in a not legal way. And the investigator used this diagram to discover that. Here you can perceive some fibers, some cluster of connections. We are still representing relationship. We are seeing that in a mortgage activity, this applicant is connected to this estate agent, and so on. We are other people around. And here there is a strong connection. You see that this is the source of a lot of connection. Applying some analytics on it with the goal of improving the readability of this radial graph, you can see very strong fiber. And you see that there are a lot of strong connection by this introducer, this lender here, this accountant here, a lot of fiber transmitted here. And this estate agent, Agenzia Immobiliari, involved in the story. And this allowed the investigators to discover the actors in the fraud. There was only one accountant involved in it, and some compiacenti estate agents that were involved in the fraud. And this way of doing it is the ancestor of what is called now chord diagrams. I will show you more in details, but the basic idea of the chord diagrams, radial graph, is to put the nodes or the data along a circle and showing the connection in an ordered way, not in this way that is not readable, but amplifying the possibility of this distinguishing connection. It is very effective. And this is used for representing different stories. There is a lot of emphasis on social networks. This is an attempt to visualize Facebook. I will show you something smarter than that with different roles. And what are the tasks above with that? We have you want to annotate the connection, you want to explain the story, you want to do some investigation like we did here. Managing visually a lot of relationship is a way for let's say arranging your information visually and having some pattern being highlighted. We have a company in England, the I2 Limited. They started in 2006, producing a sort, you see their logo, a sort of a radial representation of the data. Now it's been absorbed by IBM. And what is the basic idea? It is a very simple idea. If you like a movie involving investigators, this is a typical way in which an investigator set up a sort of puzzle on the board with the picture of the involved people, with the line showing the connection. This is the way in which you sedimentate your knowledge. In that time, that person has been arrested, but that person was in touch with this one, and this is another person that's been arrested. Here there is someone killed, or whatever is the story in this movie image. And this company, the two company, used this as a metaphor, and they set up an environment for drawing a story, connecting people, event. This is about a bombing in Africa, with people involved in the story, with the connection with the people, with picture. Basically, it's a way to give a rationale of this same idea. This is fully oriented towards relationship. The numerical value are not important here. Most of them are single entities. A terrorist, a bombing event. And here there is the storyline of the Kennedy assassination. You can see the temporal line of the Kennedy activities, or the involved couple that died, or the killer of Kennedy. You can see the timeline, some events, some point in the timeline which they are joined. I think you got this. Basically, it is a sophisticated way for arranging on a computer relationships among entities, events, people, places, plus time. There are no numerical values here, apart of the time running on the x-axis. And that brings to the short diagrams. The idea is, again, to put, as I said before, all the data around the circle, and in the connection between them represented in a nice way. Why this is? It is advantageous because you can have more room, and you can make more evident the connection. For instance, here we have, I'm not familiar with this example at all, but there is someone that is studying the brain, the human brain. You're using colors for representing different parts of the brain, and you arrange all the parts of the brain on the circle, and you can have some link representing interaction between different parts of the brain. Typically, we are talking about electrical activity. And this is the basic idea. In the way you have somehow an ordered vision of the story. You can put the label on the nodes outside. But let's see the example. This is about visualization of the exchange of goods between a nation, import and export activity. So each single country here is represented with a line. This is the United States, Germany, China, and so on. And you see the exchange of goods from United States. They are exchanging goods with Mexico, with Canada. They are very close to them. With Netherlands, no, with Japan, it's far away. With Germany, and you can perceive this exchange in terms of pairwise connection. United States are dealing something with China, for instance, and the size of the link is encoding a numerical value. It is the quantity. You can see, for instance, you can quickly get that the biggest relationship exists with Canada and Mexico. If you think about the geographical position, of course, they are in the north or the south of United States. And China is far away. And also Japan is far away. And also you have thin connection with Spain, with South Korea. It's very effective. And you can see also the Germany story. It is more complex, but it basically is with Belgium. And here the color can encode other things, the kind of the goods that is exchanged. Food, electronics, and you can also, it's not here, you can encode the direction, import or export. It is very effective. Do you remember something similar? I show you in the past classes. This kind of representation, it is called a chord diagram. You have the nodes on the circle. You have a relationship like links here, typically curved to improve readability. This is done automatically. It's not a straight line. A straight line is less effective. Plus numerical values, the sides, plus a categorical encoding. We have a color here. Maybe it is representing, I don't know exactly. It is representing some categorical value, or maybe an ordinal, or even if you have a gradation color, a numerical value as well. Basically, you have one value here, a relation here, relationship better, and the third value that is the size, and the fourth value that is the color. But the emphasis here is on links, on relationship. Do you remember something that I showed you in the past? Oh, this is the same diagram opened, in which we put all the nodes on a line. It is not readable. It is less readable. And if you draw it in a graph fashion, that will be really crowded. No clue about the ancestor of this visualization? Minor. Look at this. This was exactly the change of good between Europe and the rest of the world. Basically, it is connecting physical places instead of entities. But you can see the sides representing the amount of goods. It is exactly the same idea that we have here. And going for radial provides some additional advantages. You can do radial or radial. For instance, here we have whatever it is, I don't know. I really don't know what we are representing here, but you have entities here. You have connection between entities from here to here. We have the size representing a numerical value. We have the color representing other stuff. You can label here entities with name. And you see here, we are putting other pieces of information. Here there is a stacked bar chart that is radar somehow, representing different values. I don't know what is it, but you can go, there is room for adding other stuff. It is very common having, here you see color encoding, and here another color encoding, and so on. So you can pack a lot of information on it, but be careful to not exaggerate. You can, if you exaggerate with the putting data in a circular fashion, sooner or later you will be lost. Concentrated on the data. Let's move a little bit towards social networks. Here there is a nice example of how boys and girls interact in a school. Boys are represented with the triangle, blue triangle, and girls are circles in green. And basically, most of the girls are chatting with the other girls, and most of the boys are chatting with other boys. But here there is an outlier. Here there is a boy that is starting to interact with the girls. And this is a way of representing a social network. Again, I will give you more details about that because it is a very hot topic. But this is a nice example. Linear encoding relationship, chatting or whatever. And the colors is encoding categorical values. And they can be directed or undirected. DIAG is the chatting. It's bidirectional link. Here we have done an example. This is some experiment that has been done in the past, typically during the conferences or social events. People were wearing some electronic device, proximity sensors, and if you stand in front of a person chatting with him, the sensors were detecting each other, and you can construct complex networks of how long a person chat with another person during a coffee break, for instance. This is activity during a coffee break. A link between two nodes means that this person chatted a lot with this person. And that has been done collectively by electronic device, preserving anonymity, of course. And having this graph, you can try to figure out, you can see that it is somehow well separated. These people are chatting together, but are not chatting with people here. Here there is a cluster of people chatting together. Here there is a cluster of people chatting together, but they don't interact. They interact through other people. What is the reason for that? What is why that some people are chatting also with these people and not with the other ones, and vice versa? You can try to investigate it, labeling people with different categorical value. You can go for instance, the gender, male and female, as we did here. But this separation works only in a law school. After that, the people is not chatting with the same gender. Ethnicity, the status of your marriage, single, divorced, no. You see, no one of this put evidence in this cluster. Eventually, you can come up that the discriminant is the age. Here you're labeling the people by the age: blue less than 30, yellow between 30 and 30, red greater than 40. And you can see that older people, let's say, chat with older people or with the closer one, and the young people chat with the young people. And you can see the yellow acting as a glue between young people and old people. This is very common if you think about that. In a social activity, this is just a coffee break. People is chatting with the people with the same age. Maybe the different rules happens when your people comes from maybe different research areas in a conference, or different roles in the university, professors, researcher, PhD student, maybe that very often is associated with age as well. However, this is a nice way in which you can combine a visualization with very simple analytics to discover something. And don't forget the physical connection. Very often a relationship is just a connection between two items, like the stops of it and the ground. Let's move to maps and diagrams. Maybe you remember from the school, assume you have this data set, you are representing some hotels, and each hotel has some possibilities about facilities. They can have the swimming pool, they can have the golf, they can have a restaurant. And this is, for instance, A as both all of them, swimming pool, the golf, the restaurant. B as not the restaurant, and so on. How can you figure out of this? A Venn diagram might help. But I worked with that when I was a young researcher at university for some reason. And I discovered at that time that the situation is going to be very quickly, can be really complex. And also the order of the operators is not so easy to understand. I mean, union, intersection, and difference are not associative, not commutative. I mean, it can be a mess dealing with even with the visualization in this case. Here we have just 3 sets because you have 3 characteristics, 3 facilities. But if you are dealing with more than 3, 4, 5, that does not scale. And also this area, they are not intuitive. You have to recognize this, understanding where it belongs to. And if you have the 4th one, so the event diagram is not helping in this situation. Here we have the same visualization with more hotels. You still perceive something. Oh, yeah, this is empty. There are nothing in this intersection. Yeah, yes. Meaning that, for instance, that if an hotel has a swimming pool and a restaurant, typically here there not exist hotels that have only swimming pool and the restaurant. If you have both of them, you have also the golf. Instead, here you have someone that has golf or restaurant, but not the swimming pool. You see, reasoning on this is not so easy because these lines are not visually easy to grasp. What are possible alternatives, possible solutions for dealing with this kind of stuff? We have this solution that is called the info crystal. It is representing, if you remember, the coordinated parallel views about price, bedroom, garden size. You have the 3 Venn diagrams. And after you have a selection, a query on the 3 attributes, you have in the middle, in green, all the elements that satisfy all the conditions. In black, elements that satisfy all the conditions but one. And in gray, those that satisfy only one condition. They are all in one set. These are only in 2 sets. This is in all the 3 sets. And you can put them on a triangle. on the vertex price, garden size, and number of bedrooms, and the color are encoding satisfying only a couple of them, like this, but not the other one. This is satisfying the price and the garden size, but this is not satisfying the number of bedrooms. This is definitely more readable than this. Also, the physical position. Here, the color is helping, but this make clear what is the attributes that is not satisfied by the elements here. But again, it does not scale. And for instance, just a question for you, think a little bit. What does this one means? That corresponding to this. So you try to figure out how to deal with this representation. Do you get it? One means that there is only one hotel having both golf and the restaurant and not having the swimming pool. It's very uncommon. And here there is no, for instance, zero. Here this is an empty. This zero is better because it makes more clear the situation. Does not exist an hotel that has a swimming pool and restaurant and does not have the golf. If you have the swimming pool and the restaurant, you have also the golf, and you are here in the middle. But also this visualization does not scale. And here is the well-known solution that is called the cluster maps, in which you see you make a sort of deformation of the connection in the Venn diagram. In this way, you get rid from this confusing intersection. Here it's very clear what you have here. All restaurants that have all hotels having only the restaurant, the hotel having only the golf, all the swimming pool, or having all of them, having a couple of them. Is much more readable, and it scales also if you increase the number of features, 5, 6, 7. Here we have the example in which you have also the gym, and you discover at glance that there does not exist an hotel having only the gym. If you have the gym, you have at least the golf, or in most cases, all the other facility, swimming pool, golf, restaurant. At that scale, let's move to the last point, trees. It deserves some additional emphasis because basically trees is representing a direct relationship. You have two entities and you have a link between them representing a relationship that is a child-father relationship. So it is oriented. And they are really interesting because very often the data can be arranged in a tree. Basically, a lot of in a lot of situations you have a hierarchical structure to depict. So you have the root of the tree, you have the parents of the root, the sibling of the root till the leaf that are the leaf in the hierarchy. What is wrong with the tree? That typically they require more horizontal than vertical space. They are to draw. And a lot of effort has been devoted to draw trees and also graph. There is the graph drawing research area that is somehow overlapping with the visualization area. And there is a special focus on tree. And I'll show you some example. Something that comes from the past. We are talking about the time in which the three-dimensional visualization, three-dimensional representation were really spread. And they try to represent a tree plus circular encoding. You take the root of the tree and you put all the child of that root in a circle. In this way, you save horizontal space. But you go for occlusion. And the same down. I show you a very old movie.
This visualization, called the cone tree, shows part of a Unix directory hierarchy. Each node is a directory. When a directory is selected, the tree rotates through the shortest path to bring the selected path to the front. The selected path is highlighted with the directory name. 3D is used to make more effective use of available screen space. A 2D layout of the same tree would not fit on the screen. The user would have to scroll through the 2D layout and wouldn't have a view of the whole tree. The 2D layout could be reduced to fit, but details would be lost. Interactive animation is used to shift some of the user's cognitive load to the human perceptual system. You can see this by looking at a selection done without animation. It takes several seconds to reassimilate the relationships between the parts. With animation, the perceptual system tracks the relationships because of object constancy. When the animation completes, no extra time is needed for reassimilation.
Okay, this is very old-fashioned, but it is still a very good demonstration of a change blindness. You saw the difference between a transition without animation and with animation. If it is without, you are lost in the change. Instead, having an animation allows you to perceive the change in a better way. And here,
this vision.
No, stop. Without video, we did a variant of this, still a three-dimensional tree, but now it is arranged in a horizontal way. Why? You remember? For the sake of having more room for labels, no more than that. And in both cases, not the nice usage of shadows that give you a sort of intuition of the distribution. Also here, I don't start the movie, but I stop here. You see this shadow on the bottom, conveying some piece of information about the child level of this, and so on. But this kind of visualization are not used anymore. They're just for fun, for showing a good example of change blindness. And let's go for what is the actual winning solution. It is called a tree map. The idea is to represent the parent-child relationship. B is the child of A as a containment relationship. B is a child of A. This is quite intuitive in a single step. And you can reiterate on this. You take this tree. This is the root. So the root is the square around. After you take the child of the root, and you have this here. One child, second child, third child, fourth child. But this child has also other child itself. And using the containment, you come up with a tree map of this graph. The advantage of this is that it scales in terms of room. You can have a child and child and child partitioning these areas, and you can go for a deep level, for a large number of child without using this a prefixed room on the screen. But in my opinion, the effectiveness of this visualization is not very high. It is convenient from a point of view of the room, but somehow the degree of depth of the tree and the child-parent relationship is somehow not so evident. You need to interpret it. But it is the winner. In this moment, this is one of the best solutions we have for doing that. And you can think how to proceed. You have the containment, but in this way, in this way, in this way. And there are some technique called slice and dice, go for slice in the space, that in this way they are more suitable for including text and image. And you can have some variation. Here we have this oops, something about the calendar. You have different years. And in the year you have different child, and you going between vertical and horizontal splitting. And here we have another discussion about the different styles. Someone wrote a paper, Per Snyderman, one of the pioneers of Infovis, write a paper discussing the different possibility of arranging the containment relationship, going for squarified or slice and dice vertically or horizontally. Here I have more room for labels. And here there is an application on the web. This is Smart Money. It gives you the idea of the distribution, the proportion of stocks. We are talking about money, about stocks, about different fields: energy, financial, communication, technology, and so on. Here the idea is that the sides of a square is representing a numerical information. It is the amount of money. You can see that energy, healthcare, financial are the leader here. Technology is a little bit less, and communication, and you have transport is much less than healthcare. And you can use color for having other information. And here we have another example, still from the web, in which we have you using color for encoding numerical value. You have some filter to reduce the number of child and so on. But this is the basic idea. And the squarified version is quite popular. This paper is well before someone discovered that comparing number using square shapes performs very bad for human beings. So in this case, if you try to assess, this is more or less a square. If you try to assess the proportion between this and this, you typically will fail. You will be less accurate. And here there is another solution that I really like, still used. It is called the Hyperbolic Browser. The idea is to represent all your tree in a circle, having the root in the center. And as long as you go to the child circle, you reduce the size of the elements till the end. So you perceive the structure of the tree. And this is very interesting, because if you compare this with this is totally different. You have to get the depth till the leaf is not so easy. Here instead, you perceive the structure, but here you have not the detail, because as long as you go to the border of the circle, the size is going to be little and little till the pixel size. So you have the interaction. Here you have a company, you have the center, the big boss of the company, you have the employees, you see all the employees, and you see that this employee has a lot of other employee that is managing, she's managing. And you can, you still perceive the depth of the tree here, the number of leaves. This is an employee of a few employees. Here instead you have different branch. And if you are interested, for instance, in exploring the structure of this employee, you put it in the center. And the details of that employee will be shown, while the boss will be in a less evident position. This is the same about the Library of Congress in USA, which we are focusing on this node, but you still perceive very good, in a good way, the tree structure. And I want to show you a very old-fashioned movie, but this is really nice to me. The
hyperbolic tree browser is a focus plus context technique for browsing large hierarchies. Here we see a recent org chart of Xerox PARC containing over 300 nodes. The root of the tree is at the center of the circle, and successive levels of the tree are closer and closer to the edge of the circle. The edge is kind of like a vanishing point. Spacing gets smaller and smaller as nodes approach the edge, but the entire tree is displayed inside the circle. The structure of the tree is prominent, even when some nodes are too small to display text. For example, staff positions can be distinguished from line positions. By clicking on a node, we bring it into the focus area. Thus, we can see more of the detail in that part of the org chart while maintaining the context of the whole. We can also grab a point in the space and drag it around as we like.
Okay, that's fine. It's enough to me. You go to the animation, you go to the interaction. This is the idea. This is a very good idea, in my opinion. Still very effective, and you can easily get the library implementing it. So it is a radial drawing of a tree with a distortion of the sides in the leaf till the pixel. And the interaction allows you to browse the tree very effectively, still perceiving the overall structure of the tree. The drawback of this is that without interaction, it does not work. If you have only this, you will never know what is happening here. While this is a static visualization, providing more or less all the details you need. So if you want to present an overview in a static fashion, this is good enough. If you want to preserve the structure of the tree, this is a better solution. But you need to implement some nice interaction. So I am concluding for today, and using the metaphor of Bob Spence, we discussed already different concepts about our mind. You remember change blindness, and today we saw a new nice example of that. Deriving structure, perceptual issue we can have, very attentive values, color popping out in your eyes, brushing and linking, deriving values, and so on. And these are concepts. Here instead we have the basic techniques for representation. We have three-dimensional tree, radar chart, linked histograms, parallel coordinates, and icons, and so on. So as engineers, you can see, okay, I know this, and I am going to use it. This part is not complex, but it's something that you have to know. I showed you a lot of possibilities. All of them are standard, well known. All of them are implemented in the tree. Just use the most useful that you want to use. And I want to introduce the next part, the next class of tomorrow. Basically, the idea is that going for multidimensional data does not scale. All the solution that I provided today is for 5, 10, 50 attributes. 15 attributes, sorry. But if you have 50, 100, that does not scale. And there are some techniques for what is called the dimensionality reduction. And tomorrow I will start to discuss that. The idea is to reduce the number of dimensions before visualizing it. Maybe you are familiar with this, some of them from other classes, that's fine with me, but I will stress the visualization point of view. And to be prepared for tomorrow, just a moment. So it will be in the video. No, it's not in the video. I have to change my sharing, sorry. The class of tomorrow will be a very practical, no, not only practical, we will have some lab in it. I will describe you some principle about the dimensionality reduction, and I will show how to implement them in Python, basically using NumPy, Matplotlib, and sklearn. I suppose you are familiar with them. I'm not sure. Some of you will not. So you have to install Python on your machine, 3 dot something. If I remember well, it is 3.9 something, the last one. And you have to install all this package. sklearn, basically Matplotlib and NumPy, using the pip-install numpy, pip-install x command. And I didn't put the example on the web. I'm going to do that. I will put an example that is only to test on the classroom website, just to be sure that your installation will be enough for our need. So install Python if you don't have, install these libraries if you don't have, and run this example that I will provide on Classroom, just to be sure that tomorrow you'll be ready to run this example that I will discuss in the class. Okay, the lesson is over.